polar coordinate or spherical coordinate of the element r power alpha plus n minus 1 or 0 plus. This function is integrable if this is bounded. And that already tells you what the power should be. Alpha plus n should be larger than 0. So alpha plus n should be larger than 0, then you get integrability in our record. Right first. Alpha, yes. No. Alpha plus, if n is 1, dimension 1, and then integrability, so minus 1. Yes, I need this to be larger than minus 1, yes? Then I get integrability. Yes. So I need alpha plus n to be larger than 0. Yes, again, that's true. Yeah. So I need alpha plus n larger than 0, it means I need alpha to be larger than minus n. In dimension 1, alpha should be larger than minus 1. In dimension 2, alpha larger than minus 2. If that behavior tells you integrability. Agree? If you have the derivatives, then you have a prime of derivative of, let's say, order k. Then it is alpha minus k. And if you have the power LP, so that's a p here, so you're going to p here. And now you can do the computation, the good exercise, to see what are the conditions to get this things to work. So that tells you how Sobolev spaces are. So you're locally looking, of course this is not a complete picture because you can have this very nasty examples. But this tells you at least that most of the functions are like this. So locally, just one-dimensional integral by just going to spherical points, because you can think that, okay, this is spherical. This is the same thing. If you have an example nasty, you can always make it spherical, almost round things. And then just compute it. So that would be alpha minus k, and the power of p times p. And this should be larger than minus 1. We get integrability, and it tells you alpha minus k plus n minus 1 is larger than 1p. And this is the condition of Sobolev and Sobolev conditions. And you will actually see these things in the embedding theory and all that. So the whole idea is coming sort of. They're just simple ideas. Of course, there are really nasty examples, but this is for at the level of understanding. This is the way you should do. So do basically spherical one, absolute value of x as the best example, power alpha, what alpha should be in order to come in the right Sobolev space. The singularities is defined. All right. Actually, you can do, maybe you can do some exercises embedded with this technique. You can do that actually. Embedded theorems. Okay, so let us look at where we stopped. We stopped at the place where we want to prove the regularity theory. I think we're a little bit ahead of schedule because this was supposed to be more. So
yeah, because I think that one lecture on introduction that could be started. But it's okay, I think it's fine. Maybe we have discussion time, no discussion time.
Okay, we want to prove, so we want to prove that U is C11. Say you have to. So C11 here means that is gradient of U is Lipschitz. Are you familiar with Lipschitz concept? It means gradient of U of x minus gradient of U of y is less than constant. This is being lifted. So somehow, I want to say that the second derivatives of the function u at any point x is less than or equal to bound. Whenever it exists, it's almost everywhere. The function is already, we know, it is a W2P function, so this exists almost everywhere. But that's another question. The W2P V1, that's the W2P functions have almost everywhere C2 property. This is a good exercise. This is actually falls into the measure class. The function is in W2P, it means the second derivatives are in LP. They are at least in L1. So the absolute second derivative power p are in L1. So in L1 it means that you're falling back into what is called Pythagoras theorem. We have the measurability, and then it means that the function is going to be at this level point almost everywhere. So it's kind of have the level point almost everywhere. And that's basically it. I guess if they don't study the level point theory, no? Okay. Well, that's a good.
They don't live in measured.
Yeah. So if you look at the function which is in L1, and what I'm saying is that the second derivatives of u to power p is in L1. That function is a very nice function and has good properties. The question is whether that function exists almost everywhere. So it's like d second derivatives power p. Does it exist almost everywhere? So does it have a value almost everywhere? Well, of course, being a one function, it should have. So that's also, it's called Lebesgue point theory. Or Lebesgue point theorem. It's a search in Google Lebesgue point theorem. So you will get that any function which is integrable will get the following properties. If you take any function which is integrable, and you take integral of this mean value in r equals to 0, this is going to get g at the point 0. You get the value back, almost all z. So almost all z is this. You're actually going to use this.
Average.
If you average it, you get the point value back, but that's not almost everything. Think of the characteristic function. The function is 1 and 0. If you average, you will get the value 1 or 0, unless you're here. You don't know what you get half or something. You don't get the value back. But this is just 1 point. Measure 0 in dimension. You can think of the characteristic function, where ball rate is 1, and then 0 outside. This integral will be 1, if g is characteristic function, this will be 1 and 0. Unless you have a boundary, you don't get the value back. But the boundary has a measure which is 0, two-dimensional measure. So you realize that this seems to be working. You can do the proof of, you can actually see the proof in Google, the ABTP, that's actually. So it's called Lebesgue point theorem. Lebesgue point theorem.
So here C2 property means
C2 almost everywhere.
okay. So it is C2 almost.
It's not C2, I'm saying C2 almost.
Almost. Okay.
So this almost everywhere should have it. It's this C11, if this exists, finite almost all.
It's like if you have Lipschitz function, it is differentiable almost.
It's differentiable almost.
So here the first derivative is Lipschitz.
Exactly. That's
The second derivative is
yeah.
differentiable almost.
That's true.
That's a big proof.
Have you done it or what? Did you do it?
No, I told you that shall I do it?
Mm.
I've been asking you.
probably don't want to do that.
No, it's a big proof. I knew what to read. I have given what to read. But I think it should be done.
Isn't there other markers? And
Yes, yes.
Regarding that.
I think we got it from some lecture notes of someone. It's well written. So,
Okay. Yeah, you have to go through the other markers.
yeah.
The point is that one's looks also measure theory.
Yeah.
So let me go on with this. So what I want to prove is that this is C1 point, but we're going to realize the following. Since the function is already a very good function when the function is positive. So in the set that is positive, we have the Laplacian of mu is f for 1. We took f to be 1, just for simplicity. So Laplacian of mu is 1 when you is strictly positive. So this means that my function is actually C2 here. And then, so in this set, and this is the set when it is exactly 0, interior, I'm taking interior, 0, interior, we have Laplacian of mu is also 0. Well, I don't need to write because the identity is 0. So this together tells me that mu is actually C2. If this function is a good function, if it's an f here, it's good enough that it's C alpha, then I'm going to get mu is C2. Okay, well, in this case I get much more, but if this is not 1, it's f, I'm going to get C block or something in this. The trouble point is the bound. So, trouble is the boundaries. So that's the trouble. Okay. So what I want to do, I will do it on the board and then we will go through it on the screen. So you realize that it is enough to show that away from the free boundary, if you go away, this is the free boundary, if you go away, and u goes away, then it grows in a certain way. Now, supremum u over lower radius r and z is less than the constant, universal constant, C0, R2, and z is on the free boundary. Which is similar to u at any point x. Reverse carefully. Talking loud here. It's constant time. Here, dx is distance of x to the boundary of the set that is positive. Well, they're the same thing basically. I will maybe leave this to you to verify. Okay? And then it's enough to prove this. If you prove this, it means that then the question is whether I'm going to get what I just suggested. I'm going to get that the function is C11 over 0. I already know that's C11 in a lot of places. I don't put it free boundary as a measure 0. But there is one problem here, which we really didn't mention here, is the following. That this function is C2 in both sets. But the problem is that if this is the set that is positive, this is the set that is 0. In your point here, the function is C2, the function is C2 at this point, the function is C2 at this point, and then you come in closer and closer. So I want to show that this C2 norm has a norm. So C2 norm doesn't blow up, doesn't go fast. So think of the following function. The function is, that's the one-dimensional example. look at this function. X to the power 1 plus alpha on this side and 0 outside. Okay, the function is 0 here, so it's x to the power 1 plus alpha. This function is C2 here, do you agree? It's very nice and differentiable function. Child point is the origin. It's also very nice here. If you take the derivative of this of second order, what do you get? Then you get 1 plus alpha first derivative, and then we get 1 plus, we get alpha, and then we get x to the power alpha minus 1. So the north, that is the second derivative. So the second derivative is actually becoming larger and larger until it is 1. And I want to show that this is not happening. So my function is actually controlled. The second derivatives are universally bounded. When I say universal, because they don't care where I am. Okay? So it's universally bounded. This is not true for this function, but I'm going to prove that it's true actually for this. So here I claim only C2. I don't say it's universal. Actually, it is universal C2. If I can prove that thing. If I prove that thing, then it's going to be universal C2. So it doesn't matter where I'm standing, the C2 norm will be universally bounded. So it means that there is a constant, call it 1 billion, and my C2 norm will be always bounded like this. So whenever the function has a C2 derivative, which we know that's almost everywhere, so whenever it has a C2 derivative, that C2 derivative is bounded by 1 billion. I don't care where I'm standing. Unless I'm in a half, yeah. I don't want to go to the boundary. I don't want like boundaries outside and go over this wall. Okay, so we want to prove this. That will be the hard core, and this will actually be that. So I want to give you maybe, well, I have in the notes, so that's not going to be an exercise. So maybe I can just switch this. I like the black one much better somehow. It's easier to work on the board. So this I'm claiming would be enough to do regular. And here is the proof for you. So what we do is we take any point in the set when u is positive. So take any point when u is positive, and let me give you a picture. Of course, the picture is not so nice. It's not a very nice thing. And I'm saying that I'm taking a point y here, where the function is strictly positive. I'm taking a smaller ball, and let's say 1/4. So the whole V1 is like this one. So I'm taking a ball up here to 1/4, and this is the origin somewhere here. And then I'm taking the distance of this. So this is not true. If I take this ball, which has radius, let's call it r. So this r is dy actually. We should have changed it. This is the next thing. So take radius r is the distance from y to that point, to the bounded point. So the first time you hit. So there's the point here. So this is completely inside. Okay, so u is positive, and v radius r, and center y, which is strictly positive units. Now, if we have this, if this is true, okay, or this is true, then what you're going to get is either of them Now when I read this as an exercise. So I'm not going to do it, but they're the same thing. You will see it in the proof. You have to sort of extract it. And what happens is that what you get here is what? Is that if you put this function together, so what I'm doing a little bit of scaling. So I'm doing the scaling, so let me do it here. So the picture for us is the following. What is this? I'm sort of stretching this, making that OR rate is 1 and 0. So this is mapped to this. And then our new function, right, which is u at the point x, at the point y, plus r at the point x, and then divided by r to the power 2. R and dy are the same thing. Now you see that now this is equal to 1. So it means that the point x is going to be the polar radius 1, with center 0, and rx is a point, rx has length r, because x has length 1, so rx has length 1 with r, and the center is y. So I'm starting at y, going around with rx like this. It's the same as the whole guy here, the x is here, basically. So this guy is going to be here, and x is going to be here. It's the same. Okay. Now, if we assume the first one, what are we going to get? We're going to get the y function here is going to be less than, supremum over the whole ball is of course 2r here, with the center z here. And if I know that my solution has this property, then it means that this function is going to be less than 2 times or 4 times, something like that, constant. So I'm going to get that this is bound. And this is universally bound. So supremum of the function u tilde r, we call this the new program. This function is a new function, is defined and the Borel radius 1. It is universally bounded. It is not negative. If it would be negative, then we have to work with the problem a little different. But this is actually a simple scenario. Generally, this type of problems are a little bit simple, and when you have sign changes. So this is going to be bounded. At the same time, what do I have? You remember that the Laplacian of u was 1 with the Borel radius r in center y. So now I'm shifting it to the Borel radius 1. Laplacian is going to be 1. Nothing is changing. Because Laplacian of this function is the same as Laplacian of this function. And when we take Laplacian, this r comes down twice, because second derivative is twice and cancels. And we get Laplacian of u. So what you have is Laplacian of u tilde at the point x is the same as Laplacian of u at the point rx plus y plus r.
So here, I think that dy is r, right? Is there a mistake from
What?
then dy is
dy is r, exactly.
dy is
I
r.
don't think it-
Oh, okay.
I forgot to change it. So what you have is Laplacian of u tilde is going to be applied when you apply Laplacian, applied on the value of x. So take the derivative, the chain rule tells you r has to come out twice, and that's r2. So that r is killed with this one. So what you get is Laplacian of u at the point you have. But it means this point is always here. So Laplacian of u here is what? 1. So you get Laplacian of u tilde is actually 1. And this is a smooth function. So what do we have? It's a smooth function. Laplacian of u is a smooth function. U is universally bounded, and this is what we just learned yesterday. That the function u has to be tilde, has to be very smooth. It has to be C2 alpha. So the function is C2 alpha, or at least C2 for us, is not. So elliptic theory tells us that we get universal bound on second derivatives. So at the origin, the second derivatives of the function u at the origin, at the point y, is exactly the second derivative of u tilde r at 0. And that's universally bounded, so you get bounded. So this tells me that almost everywhere I get my second derivatives are bounded if I get this guy here to work. So I would suggest that you go through that, not in this exercise, but still like just a verification. It's a simple argument. It's a very powerful argument. So it means you're localizing things. So instead of looking at this tiny ball, you stretch it and then you have a unit ball, and then unit ball you have all of these universal elliptic PDEs. You can work. The only problem is when you stretch it, like I do there, with dividing by r, if that r is smaller, then the function becomes much larger, unless I have something like this. If I have something like this, then it means that the stretched function is still bounded. That I don't have no problem, but here I seem to have it. Well, I haven't shown it yet, but here you can prove that you do have it.
So we get so you can show for every point for the point on the boundary, for the point on the boundary of the set, this particular inequality.
Yes. So whenever you go away from the boundary, you go like a parabola. Or parabola. Like a parabola. So it's like x to the power 2. R to the power 2. You go away with the distance like power 2. So it means that when you go to free boundary, it goes pretty fast to 0, like r squared, with the distance to the power 2. And that's already a very good regularity. Think of a function. So think of one-dimensional functions. Okay, so the function is 0 here. You want to prove regularity. What you prove is that if you stay distance away, how far you have to go up, that gives you regularity. That's what we call arctangents of this angle here. So the angle here defines the regularity. If the angle is 0, the function is still 1. If the function is 0, completely taking 0 function, and the function is positive, and it goes like this, there is an angle. This function is not is Lipschitz only, okay, but it's not more than Lipschitz. But if it would be going a little bit faster to 0, so it means when you take the distance from a point to the 0 point where the function is 0, if you take this and then you look up, and you look up at this one, the value of the function, smaller value means you're better off, because it is going to go this over this. That's the arctangents of this angle, or the tangents of this. The tangents of this. So arctangents is the angle. Sorry. So you're going to get this over this. That's the sine over cosine or something like this. So that's the tangent of this angle. Of course, if this is smaller, then the sine is a small value. So if they're comparable with the distance, it means the sine theta is like theta. That's the distance you're going to get just 1. If it's going to 0 faster, then you're going to get much better. So it all has to do with comparing this distance with the value of the function. And that's exactly what it is. I'm saying we're comparing the value of the function with the distance. This is the geometric way of thinking. And if you do that, it's easier, but then technical always bothering me. Okay, so we agree that my function will be actually C2 almost everywhere. And universal C2 norm almost everywhere. So that's exactly the definition of C1. And we are remaining with this. And I don't know which one I'm going to do. I think I'm going to do this one, but I will let you to prove that they are the same. So this proof is going back to, I think it was back to, I don't know whom, but I saw it in papers by Ivan Blankens in this paper, but might have appeared there. He was a PhD student at Kepler. It might have happened in Louis Kepler's statement. I don't remember which one. So I'm not so accurate in references. But this is very standard method anyway, in the sense that when you have a PDE, you want to prove regularity. If you have a right inside, the Laplacian of U is F, and U has boundary values G. So what you do, you split the function into two pieces. One when the function is harmonic and has boundary value G, the other one where the function has boundary value 0 and contains F. So you split it. For linear cases, you do that. That's very standard technique. And in doing this, you can actually get into simpler arguments. Okay? So let us split it into two pieces, U1 and U2. I'm taking Laplacian of U to be 0, to Laplacian of 1 to be 0. That carries the information on the boundary only. So the relation with U is the boundary. That's related. Then I'm taking next function U2 to be 0 on the boundary, but I'm relating it to U inside. That's this F that we have inside. So they're related to U somehow. If you add them together, you will actually get U. Okay, this is a very standard trick, generally speaking. You split the information you have and work them separately. That might be easier. So you realize already here, if you want to prove generally regularity for the function U, and here already you see that this function is completely regular because it's harmonic. So regularity of U inside has to do with how regular this program is. Of course, here I have a radius of R, so I have to also prove a little bit of regularity for this related to R. So how is the value related to R? That's going to be important because you see, this is what I want to prove. So I have to prove that U1 and U2, they are both less than R squared. And don't forget that U is non-negative.
So Z is still the point on the boundary, I think, right? This is for
Yes, Z is a point on the free boundary.
and R.
Maybe I'm saying it here somewhere.
Yeah. Continue.
Oh, I went wrong. I went wrong. I don't know, some of them are working correctly, some of them are not. So Z is always the free boundary point. Using Z. Remember free boundary. And U is non-negative. And observe that U2 is actually non-positive. Why is that? Why is this function, let's say, negative or non-positive? Can you see that? So the Laplacian of U2 is a positive value, a non-negative value. So U is a subsolution. Yeah, agree? U is a subharmonic function. The subharmonic function has values which is less than or equal to the boundary values. The maximum at least on the boundary value. But on the boundary you have 0, so the function has to be less than or equal to 0 because it's subharmonic. So U2 is going to stay below 0. But that's a good news. Somehow thought it tells me that U2 is our picture. But maybe not completely. I have still to use that. So I can apply Harnack's inequality, which you haven't told me yet.
And do it more.
They said something about it yesterday, no?
Yes,
Oh.
just for harmonic function.
Yeah, this is
This
harmonic
one,
function.
yeah.
This is harmonic function, not general things. So for harmonic function, we have harmonic inequality, for harmonic inequality. And it tells me that, so what is harmonic? Harmonic says that if you have a harmonic function in the ball of radius 1, then let's say you're in half ball, then the supremum and infimum, and the function is not negative, then the supremum and infimum are related to each other. So if the function is, let's say, taking some value here, someplace, positive value, then in a half ball, it cannot be too big. So the value here, whatever it is, it has to be less than equal to this value times a constant. And that constant is universal. Okay, that constant is universal. So that's basically Harmonic inequality. And that already tells you about regularity, because through Harmonic inequality you get regularity. And what I told you about the distance and the values, that already tells you regularity, because if its value here is something and a little later cannot be too big, it tells me that there is some regularity here. I can extract information. And that's exactly how regularity later on is done. From Harmonic inequality, from Harmonic you get C alpha regularity, right, with a rich argument, which is actually a good training point to do that part. So Harmonics tell me that U1 at any point x is less than C, U1 at the point C. Observe that this value doesn't what it is. Okay, I don't know what the value is, but I'm saying that it's going to be less than equal to this. For any point in this book. Let's keep this in mind. We will come back and look at it again. So let me rewrite my function u, again as u1 plus u2. I have the following information. I know that u2 is less than or equal to 0. That is just so, because if the subharmonic function is 0 value on the boundary, so it's going to be less than that. So think of this. Subharmonic functions are convex functions, like hanging functions. That's how I want it is hanging. Not necessarily hanging, but think of that, like hanging crabs. Okay? In 1D, it's exactly hanging crab. And now we have boundary value 0, 0, so it has to hang below, so the value is 0. The value of the function is negative inside. So this is less than this, but we know that u1 just goes less than c times 1z. Harmonic inequality tells me this is so. And now I go back and write my function back. C times uz minus u2. u2z is 0. Okay? u2z is 0.
Let me go back.
That's what I'm trying to do.
Because u1 of z should be 0, no?
No, no.
Because u1 is
No,
equal to
it's-
u1 bound.
No, u1z is not 0.
Oh, okay, it's in
No, u2z is not 0. Sorry, u2z is less than or equal to 0. So let me go back to see. So this we use. This is the harmonics, and then this we use. And here it is. So this is less than or equal to 0. I just get rid of it.
Yes.
This is less than this. This was harmonic.
Yeah.
Okay. Now I'm adding minus u2z. Yeah. Okay. Why do I have equality here? Am I doing something wrong? Oh, I rewrite this. Sorry, this is not. Yeah, you want to use u minus u2. I'm just rewriting it there. I'm just rewriting. Because u equals u1 plus u2,
Yeah.
so u1 is u minus u2.
Yeah, so you see it is 0.
And, but u is 0. So
Yeah.
just take it out. And then I'm having minus c times u2. So what I'm doing is I'm actually relating my u only to u2. u2 was negative, but now it is minus u2, so it's positive, but I don't know how positive that is. So I need to prove that my function minus u2 doesn't grow large. But minus u2 is actually a very simple function. It is smaller than something else, which is explicit. And this is it. Okay. So it remains to show that this function is bounded by r squared up to a constant. So how do we do that? We do by binary arguments. We take a function, so now think like this. Laplacian of u, Laplacian of minus u2, okay, is minus characteristic function of something. Because Laplacian of u2 is the characteristic function, so minus of that is going to be, Laplacian of minus u2 is going to be minus characteristic function. So it's going to be like concave and then maybe harmonic someplace. I'm saying that I can actually make this even larger, take larger concave, which is explicit, and that's exactly the one. This is much larger function. So my function is going like this. My function is going and then make a harmonic something like this. I'm saying this is minus u2. I'm saying I can take something like this. This is what they call h. And this h has Laplacian of h is exactly minus 1. More super, the function is larger. So I'm taking minus 1, which is larger than minus characteristic. So I'm making the function much larger. This might be very small, super, but I'm making it extremely large. I don't care. Because this function is actually explicit. And it actually carries r. And at the point x equals to z, this disappears. Then I get r to the power 2. This may happen by 1. So what I get is that u2 is larger than s, so minus u2 is going to be less than r squared. It's going to be reversed, that minus here. And then that's it. So make it larger, but it's something simple, which you can calculate explicitly in 2 seconds. And that carries all information. And you will be done basically. So ux from here is less than that guy, but that guy is, according to this, minus you switch it, is less than c, some constant times r to the power 2. And that's exactly what we want to prove. So it says that if this is the free boundary, and if I go towards the free boundary, the function, if I walk, the value of the function drops like r to the power 2, like a parabol. Still will be a very nasty picture, but still I know that it goes parabolic. And that's it. That's the result. I know of maybe 5 different proof of this. And you can prove this very, very differently. If I go back, okay, so the conclusion is that we get C11 regularity, and you can actually prove the same things work when you get the distance. And then you make this as an exercise to prove that they are the same thing. Okay, so prove if you have this, and vice versa. So let me go back here. What am I using here? Okay, here. So I'm using my function is non-negative when I'm going to Harnack's inequality. So I can use Harnack's inequality. Okay, Harnack's inequality, this is Harnack's inequality. It can be only used if the function is non-negative. Unless you have to do other devices, but for the moment we don't have it, and Harnack's inequality is used when the function is non-negative. So now think of, if you have a problem when this function is there's still a setting of this problem where the function allows negative values, or let's say a two-phase problem or something like that. Then you're not going to get this. Then we're not going to get this proof. It doesn't work. And how much time do I have?
Half an.
Just changing the face.
Yeah, I think it's, yeah.
It's blowing. Is it blowing under there?
Did it reduce it? I thought it is much less because yesterday I was sitting here and I was feeling very cold.
It's extremely cold, but it's blowing.
Good. But tell him to reduce. Okay.
No, it's okay. I hear
That side we do.
you. Yeah, I can stay. So don't worry. So what comes next?
This came very fast.
I can do all different proofs.
No, different proof
Doesn't help.
doesn't help. But this is kind of means
You really
you can
persist?
say
No, for obstacle problem is actually this proof. If you go back and look at the literature, the proof are very complicated. You don't go through, you go through W to infinity. That's more complicated. These are quite recent, last 20 years proof or so. These are easy. There are many ways, but then you require some techniques in order to do those regularity results.
but this would be this kind of thing would be true in general, right? Wherever one wants to prove some kind of regularity.
No, you cannot use this type. Here we're using strong properties, like,
The differential equation and
yeah, I'm using that the function is not negative, for instance.
that's
Yeah.
okay. That's it.
So I'm using that function is not negative, that's a strong property, actually. Actually, we can do something else, so that can work. But let's say, I'm trying to find an idea of how I can make this a little more understandable. Because the next topic will be the reverse. So I don't want to enter into that until we get this one clear. So let's see how do I do that. So if I get into, let me do another proof. Let's see if that's going to help you. Maybe you can do part of this as an exercise. So you have already learned mean value property. Okay. So you have the following function that has an appeal to the x characteristic function of this function. And u is not negative. I'm going to give you another exercise. I'm sorry. You don't need to work. Okay. Then you can actually construct another function, which I will actually write it explicitly, but you can also prove existence of that involved with this. Construct it. But after it is to go to Green's function, but that will be really more complicated. So what we want to do is the following. I want to prove that ux is less than distance is less than constant, universal constant r to the power 2 when r is distance. So let me just put r, distance of x to the boundary of the set that is positive. Okay. So I want to prove that whenever you're here, you get the distance, this is r, then the function is quadratic. And I'm going to do a different proof. Say you don't know R is the I'm going to use mean value properties. There's some mean value properties. But I guess if you know that, then you know R is inequality. You can do R is inequality. So that's a different proof, which is actually nice. So this proof goes back to actually my supervisor almost 3 years ago. That we were working on the topic partial domain theory. Then we came up with this proof, which is a very nice proof actually. Okay, so I will erase this. So let me erase this. Okay. So I want to prove regularity. So what I do, I try to use mean value property. So let me give you a picture. This is point x. This is the distance part. I want to do mean value property. I know that this is less than equal to mean value over all of radius part, center x, and the function we want. Agree? Because the function is subsolution. Laplacian of the argument equal to 0, you can always do this. Now I'm going to make this even larger. This is less than, so there's mean value here, I think, is like 1 over r power n. With the constant, let me skip the constant. So it is like this, so it means that there is always a constant, and this. The integral of u over all of radius 2r, center z. Good? So I'm integrating not over both of radius r center x, but I'm in a log. And I'm claiming that the function, if this integral is larger than the previous integral, less than equal up to a constant. So there's a constant variable one. One is always different instance. How can I do that? If u is non-negative. So I'm already using non-negativity. You cannot do this proof if the function is not non-negative. So we're using that u is non-negative. That's the situation. Okay, now the question is, can I go further from here and do a device? So here is the device. So there is a function which solves the following problem. Is 1 minus the mass up to a constant, some constant. We can actually solve this problem, and the function h and its gradient are 0. This is in the r, 2r, center z. This is 0 on the boundary of 2r to z. We can compute this function. It looks like this. The function is explicitly something like this. If the center is the origin, it's going to be x minus z. I have to translate it 2 divided by 2n. Laplacian is exactly 1 for this. And then I have Dirac source. So it's minus some other constant maybe here, x to the power 2 minus n. I have to adjust it with an r here. So there is an r here, r to the power something. I just, here's my r to the power n minus 2 or something, or n here. Something like this. And then plus the constant c. 2 and r to the power 2, I guess. Yeah, I think it's 2. Because this will be 0 on the boundary, so they all have to have the same r. Then this is just 2 left here. But that's, we can actually compute this. This is a hand computation. So you can come up with the constant. This you don't need any constant here anymore. Laplacian is 1. Here you have to find your constant. This is r. And here you have to find your constant. So that the function has this Dirac mass, whatever it is, we don't care that much about that. This constant is more free, but this two are important. So what you do is the following. Then you have this integral over all of radius 2r and z and u. This integral, so I'm coming from that word. So this integral equals to u, so my integral u equals to this guy, Laplacian of h, because Laplacian of h is what? Is 1. And then there's the Dirac mass. But Dirac mass times the function u is 0, because center, I've chosen the center to be z. which was the center to be z. So Dirac mass at z times the function u, which at z is 0, is going to be 0. I can just write it like this. And then I can write the Laplacian of u times h, and I have to compensate. Plus Laplacian of u times h. So that integral I had at the end equals to, I just put Laplacian of h here because that's 1 for me basically. At Dirac mass doesn't bother me because it will be 0 at the origin at the point c.
That should be mod x minus z, second term.
Minus Laplacian of u times h
No, in the definition,
plus,
no, in the definition there,
Yeah.
mod x minus z.
yes, thank you. Thank you. Correct.
Okay.
It should be. Everything is as a center C, square. So this is what I'm going to get, plus this integral. So so let me erase this part so you can see it more clearly. Now, what you do, you integrate by part, and you see that this part is 0. Green's theorem, Green's identity. So if you go on the boundary, the integral normal derivative of this on the boundary, normal derivative of this on the boundary. But h, the normal derivative of h, are 0 on the boundary. So the whole integral is 0. I'm left with this. But this is 1, my characteristic function, but it is positive. So the whole thing, that h is not negative. So the whole thing is less than the integral of h, or the polar brings to rc, less than or equal to, and then divided by what? R to power 2, R to power n, up to a constant. That 1 is a different constant. But we said that h is going to be like Rn plus 2. R2, sorry. R2. You see that the volume here is compensating R to power n, so the whole thing is less than R to power 2, up to a constant. So that's another proof. Which is much easier somehow, but then you have to come up with this device, the computer, which is not bad. This works well for a point function. The other proof works for more general PDEs, just when you can split it. But this one you have to maybe adjust it differently. You can still do it if there's an invalid property or something. So, I was going to do one further proof, but I don't know if you wanted to hear another proof. But proofs have different techniques, that's the good thing. Then you see different techniques. So let me do one further proof, because you're going to need this technique. So there is a technique of blow up, when you will need. That proof is stronger than these proofs. It's much more solid, robust, and it gives you actually a better result. You can assume much less. You don't need positivity. You can assume less positivity. I will tell you. I'm not saying you need to skip it, but you can assume less positivity. These are the proofs that we started doing when I started studying this type of problems. With my colleague, Lenny Carter, did a lot of these things, playing around with it. So again, I'm putting it like this. Now I'm changing it. I'm not saying it is positive, so I want to allow it to be maybe negative later. Okay. So this equals to this, and I'm assuming u is 0 with the greater 0 in our account. And everything is in P1. So this is omega. Laplacian of u is 1 here, and then it's 0 here. The function and the gradient are going to be 0 here, and then cuts it off. Okay? And everything is in here. We know that U is C1 alpha W. Let's say half. And let's say this center is the 0 on the boundary, free boundary. This is just what we told you yesterday. The function is regular up to this order because it solves a nice PD. Let's say that the PD gives you this smoothness. I want to prove that quadratic growth, that U of x is bounded by R to power 2. When supremum of this, or the molar radius R is 0. And 0 is a free bounded point. If 0 is any z, doesn't mean 0. Any point on the boundary, I would still have this. So I'm just taking one point. So I want to prove this. Observe, I haven't assumed anything about positivity. I will come to that, what we need to assume with the vector. So we have to sort of explore it and come up with the idea of what is needed. So what I do, I say that, suppose this is not true. Suppose this is not quadratic. What does it mean? It means that when you're approaching the point 0 origin, there are certain values of r such that supremum of u on that bone is going to be like r squared from the constant, and that constant is becoming larger and larger. Because at the beginning you can assume that you know already that supremum function u is bounded by, let's say, 100. So the polar radius 1 is like 100 times r squared, r is 1. But the polar radius 1/2 is like 200 times 1/2 to the power 2. And if it's not, we say 1 billion times this. And then this just becomes larger and larger when you approach. At some point it might go also smaller, but there is at least a sequence that it goes larger and larger. Then there is a sequence Rj going to 0 such that this supremum, let me call this supremum, let me give it a name, because I don't need to write supremum all the time. So I will call this SR. SR is the supremum. Is going to be larger than or equal to R j to the power 2 times g. We agree on this? This is I think you have to just adjust yourself that this is the situation that we have. I can actually, so once I see this Rj, so let's say this is 0, so I go down to Rj and then I get the value j times Rj squared. At some point I will get this value. If I go back, it will be less. And then at some point I get this j times Rj squared. So I can say that this is actually equal to. I can stop. Agree? This is a very important point. This is actually very important. Otherwise you get very technical. So what you say, I'm standing at the radius 1 here. The value is, let's say, 100. And I'm okay. Okay. So then I go, then I go in, and then at some point it will be Rj, let's say Rj is 1 and j is 100. Rj is 1 and j is 100. Then I start going for 100 and some. Then I go in, and then at some point 101 I stand. That's my R second. And then I go in, then I stand. That's R, that j being larger. So j being larger, then there is always one value you have to stop. You cannot go in because it becomes larger than what you're assuming. You go back, that's okay for you. So you get equality exactly at this level, and then less than equal to on this. So S of R is less than equal to J R to power 2. And R is larger than RJ, larger than equal to RJ. Okay? So picture is like this. This is RJ. Here you get the value J times RJ squared. If you're here, for any R, the value is like below J times J squared. R squared. So you're below this. You're above this. Sorry, below this. Near the exact. If you go in, then you're above this. Then you go back. Okay? This is very important point. This allows you to get rid of a lot of technicalities. It is extremely simple, but you need probably, if you're not used to thinking like that, you have to take a few minutes to think about it. But let's accept this. We can think about it. So what does it tell us? It tells me that I can actually rewrite my function, like calling this u rjx plus 0. Then I divide it by j times r j squared. You see, if you go back, I'm sort of rewriting. I'm dividing by that. So when you divide it, what is the value supremum? It's going to be 1. So let's call this function uj. And you realize that actually you may even allow your function u to be different functions at each time. So that's called general, you do it uniformly for universal class of functions. But let's not do that here. So I'm just taking one function, working with one function. Then this one satisfies Laplacian of u j is what? Here's the characteristic function. I have an f here, but I skip that, and you can still have it. Doesn't really matter. But omega is not omega, it's state version. So it's going to be rjx. Okay. So you can actually change this x and put a j here. So that's state version. Okay, just state the way you don't know what it is, you don't care about it. You just state it. And then what that's? uj supremum over Bohr radius 1 is 1 according to what I wrote there. And Bohr radius 1 is exactly 1. Supremum of uj over Bohr radius r, when r is like capital R. When r is not larger than 1, is less than what? Is less than r squared. I will leave this to you to check, prove. You need to verify this. It's not a proof, it's a verification. You have to go back and then verify. So this together tells me what? Let's not forget about more information here. I have more information. U at 0, gradient of U at 0 is 0. J's. This information we have. Now, what I have is the following, that this sequence actually is bounded in Rn, at each compact set of Rn is bounded. At the Bohr radius 1, it has the supremum, which is 1. So the function doesn't go to 0, doesn't flatten out to 0. Supremum is always 1. It's universally bounded on compact sets. Laplacian of this is bounded. So this function, I forgot to say something else. If you take Laplacian of the function, what do you get here? So let's get rid of the set because it's not. It can be in there. If you take Laplacian, you're going to get rj squared divided by j times rj squared. You're going to get 1 over j. Yeah, I forgot to write. If you take Laplacian of this guy comes out twice, kills this, but j is left. We get rj squared. So this is what we get. But from here, we can actually claim the following. From here, we know that u, j converge to a function with 0 for a subsequence. So I compact this. The compactness, or Zell's type, for a subsequence converge to some function with 0, which is not 0, because supremum is 1 in entire space, function exists. Laplacian of u0 is what?
0.
Yeah, because we have 1 over j. And you realize that we cannot actually, in front of that, we can have any f which is bounded. Still, it will give 0. And we have u0 at 0 is 0. Great, u0 at 0 is 0. These are informations we will carry on. So what happens now is that if we go back to our problem, when the function is non-negative, so you have a harmonic function which is non-negative and it has a 0 value at origin. The harmonic function has a minimum, local minimum. That's impossible. So this is not possible. So the function has to be identically 0. But this function is not 0 because the supremum is never 0. So that already gives a proof for the case of obstacle problem, when you have non-negativity. Nevertheless, you can assume that your function even takes negative values, but its negative values are so small, or the domains when it takes negative values are so little that in the blow-up regime, they disappear. Think of the function being negative like in a region like this. You blow this up, that's a cusp, so this cusp will be nothing. If your function is larger than or equal to minus absolute value of x to power, what we want to say, 2 plus something, then blow up, that part disappears. So you see that possibility of application. So this is much stronger result. And you can, from this, you can get actually that. So this gives you, so any scenario you have, if u0 is larger than or equal to 0, so whatever scenario you started with, that's the reason I didn't define it. Whatever scenario you started with, if that scenario will bring you down to this situation where the function is non-negative, then you get contradiction. Principle. Okay, what is good with this technique? This technique actually can give you a lot of things, like Liouville-Path theorem. You can prove Liouville-Path theorem with this technique. You can prove the regularity with this technique. If you have an initial regularity, which is always the hard part, uniform continuity. If you have uniform continuity, you can use this, get C alpha. Okay. And if you have uniform C1, you can use this to get C1 alpha. So that uniform C and C1s are usually always the hard one. There you need real geometric way of working with this. So this is sort of cheating around and going fast, like the cars when they are going out of line. So this is what we do here. But whenever you get into the hard stuff of geometric working with geometric sets, then study is very different. But these are beautiful itself, and these are actually very nice proofs of things that might not be so obvious. I think I will stop here to pay that time. So let's take a break. Yeah? So next we will do non-degeneracy. So this is a different category of problems. Well, not problems, different category of properties. So we show that the function goes fast, but now I don't like to go too fast. So I want to contradict myself. I want to say if it goes r squared, I want to stay r squared, not faster. Because if it goes faster, I'm in trouble. I'm going to tell you that. the good news is that they don't go fast. What is the time here?
It's 3 o'clock.
No,
I don't look at London time.
no, but I don't, I mean, something to do with using track of time. No, it's-